a really, really general task. And the reasons why I think it's important are basically because it's a very broad way of looking at how to unlock human language at scale. So we're looking at large amounts of unstructured data. This could be text, could be documents that contain lots of useful information about various topics. We might also have some images, some videos, some other forms of data mixed in there. And what summarization is trying to do is extract information from all of that mass of data to try and achieve some specific goal. So we're trying to collate and combine information from these different sources to put something new together, to form some new insights. And that might be getting this mess of data through some complex model to produce some structured report or a summary down here. So summarization is a really ill-defined but very useful task to think about. And one of the kind of problems with it, I think, is that it lacks really a single, sorry, I should use the clicker. It lacks a single gold standard. So we don't have some kind of clear, correct answer for what the summary should look like when we put in these particular documents and ask the model to generate a summary. So we don't really have that, and the reason is really because I think the best summary depends on what the user is trying to do with it, so what goal they're actually trying to achieve. So what information do they need, and that depends on the user and their task and what they know already. And that makes summarization quite a hard task to deal with. So I should say, just before I go too far, if you have any questions, anything you want to interrupt, please put your hand up and just interrupt, and I can try to clarify as we go along something. So yeah, all of these different applications, different needs for something like summarization mean that we really need to tailor our summarization models to fit specific applications. And I have a couple of examples that we have been working on in our group. So the first is around generating medical reports. So this is something that many of you here will know about. So you might have very specialized kind of reports that you want to generate for a particular department in a hospital or a particular specialist. And the inputs could be not just text, but images, test results, clinical notes, and so on. So you might produce some kind of radiology report findings from the images and other inputs. A very different kind of summarization that we've looked at as well, just to show you how diverse this whole topic area could be, is around timeline summarization. So this is where we might try to extract a timeline of key events about a particular topic. So what happened to a particular person over this time, which we could look at from a set of news articles or maybe even social media posts. And we can produce this kind of structured summary of what happened around that topic. So we need some way of adapting models to do these very specialized tasks. And some of the problems that come up when we try and do that are around things like how we might use large models to solve this problem. So you can imagine trying to solve a lot of these problems by prompting an LLM to do the task, to generate the right kind of summaries. But there are some use cases where this becomes quite difficult. So in the medical report generation use case, for example, maybe we have data privacy issues that deter people from using third-party servers. They don't want to put their data in the cloud. Relying on these huge models, and at the moment they're quite cheap to use, but they use huge amounts of energy. They rely on expensive hardware. We don't know if that's going to that kind of cost is going to go up in future. And in many of these use cases, so those specialized medical cases, we might have really small amounts of data for fine-tuning a model. So if we were going to stay away from large models, we might need to fine-tune something smaller, and that's more challenging. So what we would like to do, perhaps, is then to find a way of tailoring these smaller models to different users' preferences. So this is the needs of the user for a specific task. So why I'm talking about preferences is because you can imagine that we could try to train models to do summarization for these specialized tasks using just standard supervised learning, but then you're going to need to have somebody working long hours writing all of these summaries, trying to write examples to train the model on. But it's much easier if we could generate some summaries and then judge them to say which one we prefer. That's much easier as a task, much less time consuming. So we're going to try and learn from preference judgments instead of these kind of gold standard summaries. So that could be where you present a user with a pair of alternative summaries and ask them to choose the best one. But you could also ask them to rate the summaries on a scale from poor to good. And it's a little bit difficult to be consistent about that in that case, because choosing where to put this dial, it's hard to judge where exactly to put it, and to do so consistently over lots of different examples. So it's much easier if we can just ask them to compare two summaries and choose one of those that they prefer. So we've got this kind of way of collecting data that could help us to adapt models to these specialized users. So now we need some kind of way to actually learn these users' preferences. So this starts with a preference learning model. So we have some kind of model that takes some representation of our summaries. So if you imagine that they can all be projected onto that x-axis down there. So each of the points along this line would be a different summary. And then we can map those to some kind of score called the utility. So that's the usefulness of the summary to a specific user. We want to learn that function. So for example, if we had a summary at point B there, then the score for that would be FB. The way that we can learn that is then to create some likelihood function that maps those scores, those utilities, to preference labels, so to those choices between pairs of summaries. So if you've got just a little bit mathsy here, just for a moment, you've got a summary A and it's preferred to summary B. So we can come up with a probability that A will be chosen over B in this pairwise comparison as a function of these utility scores. So if the score for the utility for A is higher than the score of utility for B, then the user is more likely to choose A over B. And we add in a little bit of this, these little terms here are some noise, and just this is needed because the users don't always select consistently with their own preferences. They may change their mind a little bit over time. They might select the wrong thing. They might not know their preferences well each time. So we have a way now of mapping the actual, those binary choices between pairs of summaries to some utility function. And so that gives us a way to train a model that can produce this kind of utility score. It has some problems though, so you get odd examples when we try and use this kind of model. So this is an example from somebody else's paper, but it's quite helpful because this is something that was generated by a summarization model that would get a high score on one of these models because the sentences that it produces are close to what the user prefers, but it's got this large amount of repetition, like just the same sentence over and over again. And there's a problem there because you've got a kind of reward hacking that's going on here. So the score, the model has found some point in that space where the summaries, the score, the utility score is predicted to be very high, but it's because none of those kinds of examples have been shown to the model during training. So it doesn't really know, so that could be a point up there somewhere. So it's got a high score. The model hasn't seen it during training, so we would consider that a kind of out of distribution case. So we've got to guard against that when we use this kind of model. So we have a model for learning like this utility score from the pairwise preferences. Now we need a way to train the model to output more preferred summaries. So this is what we can do with preference-based reinforcement learning, which is what it used to be called, but now in the literature you might see it called RLHF, which is reinforcement learning from human feedback. So that's more commonly what it's used, known as now. So you're going to use your preference function that you've learned from all those pairwise comparisons between summaries, and you're going to use that score as a reward for the model, and you can tune the model using reinforcement learning to produce summaries that are more preferred. So this, the task then for us to do to build this reinforcement learning process is to design a reward function. So we can start with putting that term there, which is from our preference learning model. So the utility that the model will give to a summary. So what we can do is then tune it to specialized tasks like that timeline summarization task. And the problem is that reward hacking issue comes up, and we need to put in some extra terms to try and counteract that. So to stop it from just producing repeated words or sentences, we add in some extra terms. And these are kind of specifying that the model should produce fluent language, not repeat words and not repeat sentences. And this is something we found that we needed to do to make it produce useful timeline summaries. So with a bit of careful design of this reward function, you can get it to produce things that basically learn from human preferences and produce much better results than just going from learning from gold standard reference summaries. So that's kind of one way that we can tune models to specialized tasks. But then another problem comes up when we start to use human preferences to tune these models, which is that sometimes they lack, they start to put errors into the summaries where they're no longer faithful to the source documents that you were trying to summarize. So we need to have some way to try and increase our faith in these summaries that our model generates, to know that they're going to be accurate. So it's still a problem with current models. So even if you use ChatGPT now, it feels good, it feels reliable. Most of the time you don't get huge numbers of errors, but you can still easily make it produce errors by asking it about things, like asking it about information that isn't really out there, that it can't possibly know, for example. And there's an example from something I was doing a little while ago where I was looking for some information on a topic, and it just hallucinated some papers. So that's, with large models, we still have this problem from time to time, even if it's not extremely frequent at the moment. With small models, so the slide mentions BART. That's a model from more than 5 years ago. It's small relative to the current GPT models, and it produces nice fluent summaries if you can fine-tune it to the task you want it to be used for, but it still makes factual errors. So it still might introduce some information that's incorrect in your summary. And then intermediate size models like Llama 3.2 and models that use chain of thought to generate their answers, they do hallucinate less than those small models, but they're still worse than humans. So we do need some way of detecting and trying to improve this kind of faithfulness of summaries. So the first thing then is probably to have some way of measuring this faithfulness or factual consistency. So different things you can do. One is to look at the textual similarity between your summaries and either the source documents themselves or some kind of gold standard reference if you have it. And you'll still see in a lot of research papers people using Rouge score, and it's just comparing individual tokens, so words or phrases, between the text and the reference. You can do a bit better with BERT score, so this is looking at the embeddings of words. And so it can capture when different words have similar meanings, but it's still really looking at a very simplistic way of comparing two pieces of information. So we might be able to do better by using natural language inference models. So these are models that can then take in your source document and your summary and try and tell you if the source document entails the summary. So this means like whether you could infer the information in the summary from the information in the source document. A third thing you can do is to use a question answering model. So this is another kind of specialized model. You can generate some questions from your summary and see if the answers that you get when you find the answers in the summary, do those answers match the answers you get from the source document? So you should find if, for example, some dates of an event are correct in the summary, then if you ask what date did the event happen, you should get the same answer from the summary and the source. So these are different ways that you might try and check for factual consistency. So they all rely on some kind of models to make these comparisons, which have their own flaws. So we've done some, and one problem is, in particular, these natural language inference and question answering models rely on you to having fine-tuned some specialized models for that particular task. So we looked at whether we could do this in a better and cheaper way by using sentence embeddings to compare the sentences in a source document and the sentences in the summary. So we're trying to compare the meaning of the sentences. So going beyond what we did with what's commonly done with BERT score, where you compare words to see if they match between the source and the summary, we can try and compare whole sentences. And this makes sense. This makes some kind of big improvement because just to take the first two sentences in this example, you've got the same sentence, but in the first case it says, I like rainy days, and the second sentence says, I don't like rainy days. So they're kind of opposite, so they're not consistent with each other. And if you compare them at the token level, then BERT score gives you this very, very high score in that 1-2 comparison there. And this SBERT score is comparing the entire sentence's embeddings, and the score is much lower. So we're detecting better those differences in meaning between entire sentences, even if the tokens, the individual words and phrases used, are very similar. So this is giving us a better way to try and judge consistency than looking just at token level comparisons. It's still not quite the best way to judge consistency because we're looking at similarity. We're not really judging whether the facts agree in these two pieces of text. Well, I don't have a solution to that question yet. But what's interesting is that those kind of metrics like SBERT score are still competitive with those much more expensive and specialized models. So using that natural language inference model or the question answering model, methods that are more directly trying to test whether the answers and the information in both pieces of text agree, they do slightly better, but they need a lot more specialized training on the kind of text you're going to use them for. And that's what those two bars there show. So they're a bit higher than our SBERT score, but not by a huge amount. There's still lots of errors and room for improvement. And there's low agreement between them. So this means that they are picking up different kinds of errors. So they're not always picking up, so most of them are not noticing all of the errors. And if we combine them, even by a simple rule where we just say, we need both our QA model and our entailment model to check the summary and see if it's consistent, to let it pass, then we get an improvement. So these are all picking up different kinds of errors, and we would like to leverage that kind of difference and diversity between them. Yeah, so we've got these kind of weak metrics for detecting factual consistency. We'd like to also be able to tune our models to be more faithful, to be more factually consistent. So we're going to look at how to do that with an approach that we've been working on. So one thing is that it's hard to ensure consistency when tuning based on human preferences only. So if you're doing what we were doing in the first part, whereas tuning timeline summaries using human preferences, one issue is that the human judges that make those comparisons often forget to check for factual consistency, or it's not the first thing on their mind. They're not checking every single piece of information in the source and summary. They're looking at whether the summary reads well and whether it sounds useful. So what we're thinking about doing here is, instead of using human judges for this part, is to try and use automated metrics to kind of back up those human judgments. So we've got a whole collection of robot judges. And so these are these different metrics that are assessing factual consistency. And if we can label preferences, pairwise preferences, using these different weak metrics, and we can pick out the cases where they disagree with each other, and we can discard those labels. We think that those are probably unreliable. We could then learn from this crowd of robot judges to overcome the deficiencies of these individual metrics. So to do this well, it really matters what we ask people, or what we ask the metrics to compare. So we start with a pre-trained summarization model that's reasonably good at doing general summarization tasks. And that already doesn't make big, obvious mistakes. So we need to improve it, we need to generate some examples where the mistakes are a little bit more difficult for the model to detect. So we can do this by trying to generate lexically similar summaries, so summaries with similar words and phrases and topics in them. And we do this by varying the decoding strategy in our model. So we've got this generative model, and we can generate summaries using a few different kind of sampling processes. If we choose two good summaries from this model, we get two summaries that probably don't contain any really obvious major mistakes, but may contain some small factual differences. And we can then use our robot judges, our weak factuality metrics, to label them and to judge which of those is more factually consistent. So we then have a set of these kind of noisy preferences from our automated metrics, and we want a way to try and combine them together and train our model from them. So if you remember before, when I was training the timeline summarizer with reinforcement learning, we had to design this reward function that was quite complicated. It had a number of different terms in it. Oh, is that gone? Ah, sound has gone. Oh, it's back. I think it was just... Hello? Yeah. I think it might be slightly loose somewhere. Okay. We can try and avoid that complexity by skipping reinforcement learning altogether. So we can use direct preference optimization instead. So this is a method. I'm not going to explain it in too much detail right now. It's a method that's now quite widely used. Maybe some of you have already used this. But it kind of avoids the need to design this reward function, so we can directly learn from those pairwise preferences. And so I guess a key part of it is a loss function. Without reading it too much, you've got these two Fs in here, and those are like the utilities that that we had earlier in that preference learning model. So you've got a utility score for the winning summary and the losing summary, and this training process is looking at the differences between those two scores. So it's trying to make it so that the winning summary would have a higher score than the losing summary, and these scores basically represent the likelihood of the model generating that summary. So in training it this way, we're going to get the model to be more likely to generate these winning summaries. So the result of doing all of this is that we can get our smaller models, like that 5-year-old Bart model, to be just as factually consistent as some much more recent models. And that means that we could, if we use this process of collecting human preference data and use these weak metrics for assessing factual consistency, we can tune these much smaller models, much more lightweight models, to new tasks and specialized tasks. And without diving into this too much, there's lots of different categories of errors we can also look at. And we can try and investigate where the models are still making lots of errors and where those error rates have decreased. There's some more information in the link, which I think we can share later. So just looking at the time. So I think I've covered quite a few things already, but one thing that I think is quite important is to consider how we get these human preferences and how we might do so efficiently. So if you're trying to adapt your summarization model to a specific use case, perhaps you only have one or two users that you can actually ask to create these labels, to make these judgments. So we need to do some kind of efficient preference labeling. So yeah, if we're thinking about this task again, we're asking people to choose between these pairs of example summaries. Now, in like the standard RLHF data sets that are used to tune these models, you get tens of thousands of annotations, and we can't really compete with that if we're trying to ask a few doctors to help us train a specialized summarization model for a particular medical use case, for example. So we want to really be able to personalize a model with even just a handful of labels. So what we could do is to start from a model that's already fairly good. We can generate lots of candidate summaries, and then if we carefully choose which ones we ask the users to compare, we can try to maximize what the model learns. So I think when I was putting that image in there, which is a bit strange, someone's juicing some lemons. They're trying to squeeze the maximum out of a very small number of labels, get the most information from it. So instead of just using loads and loads of labels, yes.
Question from the previous study, I guess.
Oh yeah.
So you have the automatic judge, basically,
yeah.
Scoring reward function, and also you create your own training data from a bigger summarizer, right?
Yes.
So in a way, you're distilling from
yeah.
a bigger summarizer into a BART-based.
Yes.
Model, right?
Yeah. So, well, I guess you could. I suppose it would depend on how you get those pairwise judgments, right? Because if those preferences are coming from a large model, then I think it would be a kind of distillation. But in the case that we're using there, we're mostly using other fairly small models. So the natural language inference models and question answering models were only, I'm not sure what the question answering one was. The NLI one was a BERT-based model, so it's also a similar size. So I guess we're combining information, it's sort of distilling it in a way. But, yeah. Okay, so, thinking about getting information from different things. Here, getting information from the people. And we're trying to choose which pairs they should label to get the most information. So what we can do to maximize what we learn is to consider uncertainty when we're choosing the pairs we show to the people to label. What we've worked on in the past, mainly a few years ago really, was to use Bayesian approaches which measure the uncertainty in this utility function. So instead of just having a solid line here to give us the score for each summary, we've also got this band around it, which is the variance in that score. So this is telling us how uncertain the model is about what that score should be. So for that point that's marked for XB, the model is quite certain. It kind of knows what the score should be, but these areas over here, it has high uncertainty. So that's an area where if we ask the user to label some examples there, we might learn a lot more from those examples. So those summaries with high variance could be seen as out of distribution, where we might need more preference labels. In contrast to these points with low variance, which are already quite well known. So we don't need to waste the labeling effort on those areas that are high certainty. And we're instead going to focus on low confidence areas. Oh wow, I forgot I had so many annotations here. So instead of just giving us the score, this FB, we've now actually got a whole probability distribution for each point. So that probability of FB, you've got a mean and a variance, and it has a Gaussian distribution for that particular summary. So we can get those variance estimates by using approximate Bayesian deep learning methods. The simplest one that we can use that is quite effective in our experiments is Monte Carlo dropout. So this is using dropout in your neural network, but you turn it on at inference time, and you run your model multiple times, say 20 times, and produce 20 different samples of what that utility score should be, and you can estimate that distribution from those 20 samples. So that's good enough, even though that's quite a rough approximation, that's good enough to get some useful estimates of the variance at each of those points. And then we can use that information to help us choose the right pairs for our user to label with Bayesian optimization. So the goal here is to find the area of that function which has good summaries, not to learn the whole function. We don't care about learning the utility score for summaries that aren't very good, because we're never going to try and produce those. We want to just learn the best outputs. So what we do is use this iterative process where we select a pair, we label it, and then we retrain our ranking function, this utility function, and then we repeat. So the way we select it is to choose the current best example. So the one that we estimate is the best according to our current model, and we find another candidate, A, that maximizes expected improvement. So this is using that function that includes probabilities over utilities to try and estimate which point will bring the biggest increase in utility. So this considers both the mean of the estimate. So at point A, it's got a current utility estimate which has a mean that's very, very similar to point B. So point B is our best, but point A is pretty close already. But it also has high uncertainty. And so that means there's a very good chance that if we learn more about A, it might actually be better than B. So then we request the label from the user, and they say that A is preferred to B, and we update the model. So we retrain it, and you see that the function has now increased for A, and the uncertainty around that point has gone down. So doing this turns out to be a really effective way to get big improvements to our models from just small numbers of comparisons. So this is not for summarization, but for a question answering task where you have to choose the correct stack exchange answer to a complex question. And using this kind of expected improvement method gets us big jumps in accuracy just from like as few as 4 pairwise comparisons. So I think this is a method that we should be looking at using more widely and could be adapting to other sorts of use cases in future. Yeah, just keeping an eye on the time. I have one little section to go. I think I can fit it. So we've been talking a lot about adapting to individual preferences, but I'd also like to bring in some work that we've done around crowds as well. So we're often collecting preferences not just from a single person, but from multiple annotators. You may see large data sets in NLP that have been collected from websites like Amazon Mechanical Turk, but there's lots of more current crowdsourcing platforms that people use to collect data. Because it's cheap, it's scalable, you can get lots of labels very quickly, but you have to use multiple labels for each item to mitigate the errors that might come from using untrained people to label your data. And there might be an issue with using preferences because they're very subjective. So how we might learn from a crowd in that case. So we have a couple of models that we've developed that can help us to do that. So one of the things is to learn about how individual people in that crowd label the data. So to try and model those individuals and use that model of each person to help us better infer the overall preferences of the crowd. So if we imagine that there is a kind of underlying overall score for each summary that we want to rank, we can try and predict that by modeling the individual preferences and adjusting for that to get this overall score. So we have a model from a few years ago called CrowdGPPL that models personal preferences as an adjustment to the overall score. So just to give an example of what it's doing, if you imagine that one person prefers a less complex summary, and we have two summaries here. One is more complex, one has less detail. We have a person who gives this personal score, and we have another person, we have a person who gives, the same person is giving this, higher score to the less complex summary. However, the overall score that the crowd as a whole would judge for this summary is actually the same. So this person has a kind of negative adjustment for the more complex summary and a positive adjustment for the one with less detail. So basically, we're trying to learn this through the pairwise labels from different people. And by doing this using, again, a Bayesian approach, we can learn the way that we need to adjust the scores for each person to infer an overall score. So just this idea of like modeling individuals in the crowd and getting better results from it extends to a lot of other kind of data beyond preferences as well. We can look at classifications and labels of sequence data. One of the problems that comes up quite often is that when people label classification data, you get a crowd of people to provide the labels, and then you take a majority vote. So trying to mitigate the fact that people might disagree on what the correct label is. Unfortunately, if you just use majority vote, you're ignoring the differences between those people and how accurate they are and what different biases they might have. So instead, what I would recommend to do here is to use one of a whole range of models. Most of them are based on something proposed by David and Skeen back in 1979, and we have a lot of variants of this that have been developed much more recently. And you can use those to get some kind of gold standard data from the crowdsourced classifications. What they do is basically model the likelihood of each label or annotation from each individual labeler given the true label. And this allows us to deal with the fact that some people have a higher error rate than others or are more biased to one label versus another. So for example, this is plot for an imaginary labeler in a crowd on a binary task where you have to choose labels between 0 or 1, and this person has a bias towards choosing the label 1. So here, if the true label is 1, they almost always choose the correct label. But if the true label is 0, they may also choose the label 1 and get it wrong. So you've got some differences, some imbalance in how their error rate is on each of those different true labels. So if we use these kind of models, we can get quite big improvements in the quality of the data we get from crowds, from combining crowdsourced classifications. So just to give one example of this, in named entity recognition, we could use this kind of model to infer the true labels from crowdsourced labels using this kind of Bayesian combination model. And you get across several data sets, using our approach, you can get a big increase in the accuracy of the gold standard labels that we get compared to picking out the best worker from the crowd or taking a majority vote between the people with equal weighting. You could also use this kind of approach to directly train a neural network with the data from the crowd, so you don't have to go through this annotation process of making like gold standard data to train your model. You can train it with noisy data from a crowd directly. So this comes through some kind of complex looking diagram. So you've got a crowd producing some labels. It's going through a neural network with its crowd label attached. It's going through the crowd layer to try and infer the true labels. Those are then fed into the model, and the model's predictions are fed back into the crowd layer. And there's an iterative process that lets us train this model directly from the crowd. So the key message there, I think, is not to throw away individual annotations because they can be really helpful when you're training a classifier. But when you collect data, to collect all the information from individual people and keep that information, keep the IDs of the people who've provided the data. So I think reached the conclusions. So just to give some overall kind of thoughts, I think these small models can be really faithful and accurate and very useful for specialized use cases if we train them in the right way. So we can do this by making use of weak evaluation metrics, combining them together to create stronger learning signals. We can tune models to noisy human and automated feedback via preference learning. So this helps us deal with tasks that are difficult to get gold standard training data for. I think it's really important to account for uncertainty. I mean, in the cases that I showed just now, to help us avoid out of distribution errors, but also optimize the process of collecting feedback. The disagreements in the crowd carry useful information. So this is something to bear in mind. The differences in the labels that people provide in preference learning and crowdsourcing in general are really informative. Okay, so I think, briefly, what I'm thinking about next is how we can use this kind of Bayesian optimization approach to cut the cost of reinforcement learning from human feedback, using armies of weak labelers to tune our models, creating more user-friendly tools for adapting small models using some of these techniques. So we could do things like generate personalized health reports with our own individual preferences. And how we might go from these pairwise labels to collecting preferences through dialogue, through conversations with a chatbot. Okay, cool. So I think I have reached the end. Thank you all for listening and sticking around. And I'd like to thank my students and my collaborators who've done all of this work, and leave you with some pictures from Bristol in case you would be tempted to visit us one time.
Thank you so much, Edwin. Any questions from the crowd?